Tapered rear axle shafts were used by Ford, Chrysler, Willys, Studebaker, and other manufacturers. Tapered axle shafts mean that the hub and drum assembly need to be removed periodically to service the vehicle. Most damage to these threads is from abuse by a hub puller during brake and other axle service work. The conventional pullers place high loads on the axle shaft end, including brute force from hammering on the puller stem to shock the tapered hub into releasing from the axle shaft. Even a shaft with reasonable thread nose stamina will yield under this kind of force, causing thread or cotter pin hole distortion or fractures. This can be avoided. See the easy-to-make tool remedy at the end of this how-to coverage. By design, this shaft has no nose protection. The threads in the cotter pin hole were even more vulnerable. Fortunately, the damage is confined to the cotter pin area and the outer portion of the threads. This is induction or case-hardened material, and simply trying to restore the shape of a mushroomed hole will not work. Fractures will result. Since this is not a structural high-load section of the shaft, repairs can be made to the damaged outer threads. Rebuilding the entire thread section will not be required, and brazing is the practical solution. Fractures should be cut to the root and end of the fracture. The Dremel diamond cutting disc has just the right width for a high-quality bond and fill with weld mold 85C brazing rod. Distorted threads must now be aligned. To square up and align the threads, we use a Ness tool before starting a die. The Ness thread chasing tool will trace a pattern from an existing intact thread. Do not cross these threads, or the only option will be full restoration steps for the entire end section of the shaft. Cost-wise, this is seldom economically practical and involves sublet normalizing at a heat treating shop, buildup of matching weld filler with bona fide fusion welding, machining and thread cutting in the normalized state, and reheat treating or case hardening of the entire shaft, or at least the shaft thread section if the shaft was only partially normalized with the rest of the shaft masked off. Before incurring such labor and sublet costs, it would make sense to find another axle shaft. Here the die is used more like a thread chaser than a cutting die. The aim is to stand and align the threads rather than cut material from them. Between the NES tool and the die used as a chaser, maximum material remains in place. This is the OEM castellated nut used to check and confirm the alignment of the threads. Close examination turns up this hairline fracture. Cotter pin support requires stable threads and end section integrity. The small fracture will also be repaired after redrilling the cotter pin hole. Temple stick heat crayons serve as a monitor of heat applied to the shaft and thread section. 1500 and 1150 degrees Fahrenheit are wide boundaries to be measured. A 1450 degrees Fahrenheit temple stick checks for heat right at the annealing threshold. Thermotrap paste coats and protects the surrounding metal up to 1600 degrees Fahrenheit. This is a highly effective heat barrier that also protects sensitive parts in smaller assemblies. Thermotrap actually absorbs heat. Here, the threads are aligned properly. This hardness test file set provides a baseline before test of the shaft, thread, and keyway hardness. The tool set was purchased under the Fowler brand at Amazon.com. These files will help determine the original induction or case hardening, providing a quick, accurate measurement. This is an optimal tool set for a smaller shop or professional welder fabricator who does not have the demand for a $1,600 to $3,500 professional rock weld tester. These compact and portable HRC files represent 5-point increments from 40 to 65 HRC. The HRC test can be conclusive if performed properly. Here, the aim is to compare hardness before and after the brazing operation. In addition to the temple stick heat crayons, a drop in HRC or hardness will help determine whether the annealing temperature was reached, compromising the thread or shaft integrity. If a file is unable to scrape metal, the surface is harder than the file's HRC rating. Leaving a file scratch indicates that the file is harder than the metal surface. The pretest hardness is in the 60 HRC range. This would be consistent with the case or induction hardening of forged 1050 carbon steel, which is typically 58 HRC plus. The 60 HRC file does not leave an indentation scratch mark. The 65 does. The hardening is over 60 HRC and under 65 HRC. Thermotrap paste is a highly effective barrier to heat. All critical areas can be protected from heat absorption. The paste helps prevent heat buildup and damage, staving off risky temperatures that approach the annealing point. Heat can be isolated and concentrated at the braze area. This paste can protect to 1600 degrees Fahrenheit. Temple stick crayons show whether a specific temperature has been reached. Temple stick crayons are popular with welders and others who do field tests of metal heat. Each crayon will melt at the precise temperature indicated. For this project, one temperature in particular is important. 1450 degrees Fahrenheit is the lower end of the annealing zone for 1050 carbon steel. Weld Mold 85C braze filler melts at 1400 degrees Fahrenheit. This is a narrow window to be monitored carefully. Weld Mold 85C has been purposely chosen for its unique bonding characteristics. The bonding temperature of 1400 degrees Fahrenheit works well with this project. If strength were our only concern, Weld mold 26C would be the choice. However, 26C has a considerably higher melting and bonding point. Bonding at 1600 degrees Fahrenheit, weld mold 26C would be well into the annealing zone for this 1050 carbon steel. On film, the cone of this number 2 torch flame is unclear. It is actually a neutral cone. Weld mold instructions call for a neutral flame held 1/4 inch away from the base metal on a low angle. This method dramatically reduces the heat input into the base metal, which is another reason 85C was selected for this project. Heat control is of paramount importance. Knowing the colors of metal at various temperatures will help. Study this chart. This is the visible field for colors of heated metal. There are other guidelines for determining the heat of metal being worked with a torch or welding equipment. This chart, however, is a real-world, realistic indicator of temperature as viewed by the eye. Uniquely, weld mold 85C does not require wetting the base metal during the brazing process. This is desirable since our aim is to reach but not exceed the bonding temperature of 85C. Note that weld mold 85C is a true brazing rod. This requires bonding, not fusion, as in fusion welding. Fusion welding of any type would destroy the heat treatment. If a fusion weld buildup is required to repair the end section of this shaft, the shaft would have to be normalized first to remove heat treating, then welded and machined, then reheat treated. The welding nugget and heat affected zone around fusion welding could be easily 1000 degrees Fahrenheit higher than the brazing temperatures we're working with here. As a rule, heat treated metal should never be fusion welded. If the metal needs welding repairs, the metal must be normalized before welding. Moving the torch at or near the melting point and bonding temperature of the braze helps minimize heat input into the base metal. Again, the aim here is to hold the peak heat in the base metal at 1400 degrees Fahrenheit. This temperature peak should be limited to the bonding area of the braze and not applied to adjacent metal. By not reaching and maintaining the annealing temperature, the combination of taking the braze to its 1400 degree Fahrenheit bonding temperature plus use of thermotrap paste keeps the base metal adjacent to the braze area way below the annealing and normalizing temperatures. An infrared heat sensor is practical. Immediately after removing torch heat, the shaft and thread temperature can be tested. Thermotrap, weld mold 85C filler, and the recommended low torch angle minimize the heat input to the shaft thread section, which measures from 180 to 389 degrees Fahrenheit range right after torch removal. The actual brazing zone heat reads 720 to 750 degrees Fahrenheit when measured quickly after the brazing procedure. The actual braze bond with 85C, again, takes place near 1400 degrees Fahrenheit. Carefully directed heat, often applied through the braze material, allows the bond to take place at the precise bonding temperature. This dramatically lowers the input temperature to the base metal. Low-angle heat, with the neutral flame cone held 1/4 inch away from the base metal, keeps heat input to the shaft and threads in check. The torch is moved in a calculated manner to localize heat and draw the filler along. At no point is this base metal, forged 1050 carbon steel in this case, allowed to overheat. Note that the thread section between the cotter pin hole and tapered axle section never reaches visible red during this repair. The heat-treated base metal at the repair section matches the 1375 degrees Fahrenheit zone when viewed in shop daylight fluorescent lighting. Peak target temperature is 1100 degrees Fahrenheit or less everywhere except the braze bonding margins in the repair sections. Brief moments of 1375 to 1400 degrees Fahrenheit do not impact the heat treatment. Using this color chart, bright cherry, salmon, or dark orange is the anneal heat zone for this range of carbon steels. Full orange would be the normalizing heat zone that removes all heat treatment. Color will often appear in the flux stream and should not be mistaken for red metal. The actual braze bonding zone with 85C may briefly reach into this chart's cherry range at the braze bond margins. When working with carbon steel, know the various shades of red leading to visible orange. Case and induction hardened carbon steels will lose hardening strength at distinct heat color ranges. On this project, the braze bonding occurs right below the annealing temperature. Forged and heat-treated 1050 carbon steel anneals between 1450 to 1600 degrees Fahrenheit. Always know the specific metal's annealing and normalizing temperatures. Know the bonding temperature of the braze filler. If too much heat is absorbed for enough time, the case hardening will deteriorate. Annealed carbon steel is significantly softer and lower tensile strength than the engineered standards for these 1050 forged and heat-treated axle shafts. Pay close attention to the bonding temperatures of braze rods when trying to preserve heat treatment. Brazing with weld mold 85C, 1400 degrees Fahrenheit bonding, is the heat exposure limit for this 1050 heat-treated carbon steel. Any fusion welding process would require more heat and cause annealing and normalizing of the workpiece. Heat treatment and high tensile strength would be lost. Attempting to fix this thread section with MIG, arc, or oxyacetylene fusion welding using ER70 S2 or S6 type rod would be a mistake. Silver brazing, use of 6011, 6012, 6013, or hydrogen 7011, 7012, 7014 type rods would also be a mistake. All of these processes would be fusion welding and much higher temperatures than the heat treatment could tolerate. The molecular structure, strength, and integrity of the metal would be ruined. Axle shaft threads are a safety concern. Built-up buttons at the shaft ends will simulate the better-built axle designs, providing more reinforcement of the cotter pinhole and better protection when using a hub puller. The best thread protection is a tool similar to the one illustrated at the end of this coverage. Notice that heat in the red zone is held there only briefly. The chart's cherry color is 1375 degrees Fahrenheit. This is just about the bonding temperature for 85C. We want it no hotter than this color. Apply just enough heat to melt and bond the braze to the base metal, no more. Additionally, heat is applied through the braze filler when possible. This heats the base metal to the exact melting and bonding temperature without adding unnecessary heat. Weld Mold 85C does not require the usual heat-absorbing wetting of the base metal. 85C was selected to minimize heat input and protect the hardened shaft and threads. The temperature, measured immediately after torch removal, confirms that heat has been isolated. The heat has been kept in the braze area by drawing back on the torch, confining heat within the braze button. Absorption of heat into the base metal has been restricted. Actual heat exposure at the axle shaft base metal is well below the annealing temperature. Hardening and heat treatment remain undisturbed. The button is not a load-bearing portion of the shaft. Its purpose is to strengthen the end and restore appearance. Temple sticks and HRC hardness files are verification tools for confirming that the original heat treatment and hardness is unaffected. Quick end grinding perpendicular to the shaft threads puts this button in rough form. 85C files well, though the material's Brinell hardness, which reaches 220 BHN in work-hardened pieces, becomes evident. With a clean starting point, proper manipulating of flux and heat, there are no voids or porosity anywhere in this braze buildup. Bonding is complete. This is the NES thread chasing tool. Its blades can trace existing threads to create stable, uniform thread repairs. Here, the tool has picked up a lower thread in good condition and uses that as a pattern to run the second cutter to the top of the threads. This creates a pattern that the die will follow later. The gnashing noise is threads being cut into the flux end brazing material. Look at the die from the top side and the bottom side. All angles to make certain that the die is tracing the actual threads. The success of this entire project rests with making certain that the die is following the original threads and not removing critical material. The die is used to chase the threads rather than cut new ones, and only a minuscule amount of metal gets removed. These are hardened threads that need to maintain their shape. The nut torque is 140 pound-feet minimum, which requires proper thread mesh. This thread damage can be avoided. At the end of this coverage, see the easy-to-make tool that prevents this kind of damage. The cotter pin hole can be drilled on a milling machine. With care, a drill and drill motor can do this job. Be certain to align the drill bit squarely with the cotter pin hole. The castellated nut can be used as a guide. Do not damage the castellated nut and keep the drill bit running squarely through the cotter pin hole. Do not remove excess material, and in this case, the drill bit is an 11/64 inch diameter, slightly undersized for a 3/16 inch cotter pin hole. The cotter pin will fit snugly. The button brace buildup also fills the indexing hole at the end of the shaft. This reinforces the area that was cross-drilled by the OEM. The brace buildup is now a stronger section at the end of the thread. Let's quickly run through the steps on the second shaft. We'll speed up the film rate. The NES tool has traced a thread that the die can follow. When starting the die, use extreme care to make sure it's square. This is a critical moment. The threads cannot be cross-threaded. Make absolutely certain that the die is catching the original threads below the braze buildup. Note how once on square, it takes a very slight amount of pressure to run the die. Tap Magic oil is expensive, but well worth it. The use of this oil with the die minimizes the removal of material. We want to maintain material intact. In this case, the die is used just to chase the original threads. The shaft thread material is harder than HRC 60. The 60 HRC file does not remove metal from the threads, either in the original thread section or the repaired section. This indicates that the material is harder than 60. HRC 65 is now tried and does remove material slightly. A guess would be that this material is 61 or 62 HRC. It is distinctly over 60 HRC and consistent with the OEM hardened surface. 1050 carbon steel, when it is forged and heat treated properly, is usually in the 61 HRC range. 58 to 62 would be acceptable. What we're discovering here is that there is no impairment to the original hardening. The brazing process with Weld Mold 85C was successful in maintaining the original hardening of this thread section. The temperature and heat absorption were kept below the annealing point, and the metal has OEM integrity. The combination of thermotrap paste, 85C's relatively low bonding temperature, no wetting requirement to create a brazed bond, and careful manipulation of the torch with a number 2 tip each helped preserve the hardness and integrity of this metal. The gaps created by the Dremel tool and diamond wheel were ideal for a high-strength repair. Use of the 40 HRC through 55 HRC files shows that none of these files can scratch or indent the metal in the original or repaired areas. The entire workpiece is harder than 60 HRC. Lesser hardness files do not leave a mark. The original heat treatment has not been damaged. Now we test the second axle shaft. All areas of the second axle shaft also test above HRC 60 and likely 61 or 62. This is a finished product, restored and fully functional thread set on both axle shafts. Each axle shaft will provide safe and reliable service. All of this kind of damage can be easily avoided. Here is a solution, a simple tool. The internal threads match the threads on these axle shafts. The lug nut has a forward shoulder that is squarely machined to match the shoulder of the tapered axle. Do not overheat this tool when grinding or cutting the outside edge. This is hardened steel and must remain hard to be a functional tool. Wear goggles or a face mask and use gloves when grinding this hard steel. By design, this tool places the press load against the shoulder of the axle shaft and not the threads. The threads merely align the tool and keep it in alignment. Two important additional functions of the tool are to set the location of the key in the keyway, and also, when threaded onto the threads before removing the hub, this tool will prevent the hub and key from causing damage to the threads. The key can be held in place. When the hub is removed, the key will not move outward and gouge the threads. Aligning a square key in a keyway is a critical job. Be certain to follow the OEM guidelines for locating the key in the keyway. The key must support the hub properly. If not, the hub can become damaged, and so can the keyway. If necessary, the square end of the tool can be drilled with an index for the hub puller stem. The index should match the tapered point on the stem. Always follow OEM guidelines when servicing axles, bearings, or brakes.